Hello, back again with videos. And today we're going to learn about the probability of independent and dependent events. So that's going to be our vocabulary today too. Alright, so Raji and Kara must each choose a topic from a list of topics to research for their class. If Raji's choice has no effect on Kara's choice, and vice versa, then the events are going to be, which vocabulary term do you think? Independent. For independent events, the occurrence of one event has no effect on the probability that a second event will occur. If one of Raji's if once Raji chooses a topic, Kara must choose from the remaining topics, then the events are dependent on each other. For dependent events, the occurrence of one event does have an effect on the probability that a second event will occur, and we'll look at one of each. Alright, so right now we just want to decide if they're independent or dependent. And so the first one, Kathy draws a 4 from a set of cards numbered 1 through 10 and rolls a 2 on a number cube. Those are two separate events. They're not going to affect the other, so that would be independent. Second one, Yuki chooses a book from the shelf to read, and then Jeanette chooses a book from the books that remain. Well, depending on what Yuki chooses, it's going to affect Jeanette's choice, so that is dependent. And then C, Joanne flips a coin and gets ahead. Then she rolls a 6 on a number cube. No effect on each other, so that's independent. And then D, Annabelle chooses a blue marble from a set of 3, each different colors. And then Louise chooses a second marble from the remaining 2. So that means it's going to affect it because it's going to depend on what she chooses in the first one. All right, so now to find the probability that two independent events will happen, multiply the probabilities of the two events. And I'm sure you're wondering why. Well, I'll show you after we do the example. All right, the probability of two events, probability of A and B, will equal the probability of A times the probability of B. That's just the mathematical way to say the definition. All right. So find the probability of choosing a red marble at random from a bag containing 5 red marbles and 5 white marbles, and then flipping a coin and getting a heads. All right, so these are, there's no effect one on the other, so they're independent. So the probability of red and heads is going to be probability of red times the probability of heads, which is 1/2 times 1/2, which is 1/4. Now, to look at that on a tree diagram, like we did in our last chapter, or last section, that's going to look like this tree diagram right here. So we have the number of marbles. Okay, there's 10 of them, so I wrote those out, 5 red, 5 white. Then the effect on the coin, well, 2 outcomes, head, tail, all the way across. So that's 20 outcomes. Well, that's counting principle, 10 times 2 equals 20. So we've got a denominator of 20. Well, how many of these then occur? Let's see, with probability of reds and heads. Well, red head, there's 1. Red head, there's 2. Red head, 3. Red head, 4. Red head, 5. So that's 5 parts out of 20 wholes on the 20 outcomes. And that reduces to 1/4. And that will happen every time. And that this is another way to do it. It's a lot faster to use the idea of probability of independent events, being just multiplying the two probabilities separately since they're independent from each other. All right, to find the probability of two dependent events, you must determine the effect that the first event has on the probability of the second event. And in that case, probability of A and B equals the probability of A, that's the first event, and then times the probability of B after A has been done. Okay, so let's look at an example of that. Okay, a reading list contains 5 historical books and 3 scientific books. What's the probability that one will randomly choose a historical book for his first report and a science fiction book for his second report? Well, he can't pick the same historical book and do a report on it twice. So he's going to take one book, and then there's going to be one less book on the shelves, and then he'll have 7 to choose from after he picks one. And they want to know the probability So those are dependent on each other. We want the probability of historical. And then when we look at, if we take a historical one, then one of those is gone, and then there's left 3 science fiction and 4 history books. So that's going to be 3 left out of 7, so that's 3 sevens. And then if you multiply these two probabilities, you get 15 out of 56. Probability of A, and then the probability of B after A, which means you've taken the A, one of the history books, out. All right, so what does that look like if you were to look at, now that's huge if you look at a tree, so I didn't do the whole tree. But the first book, there's 8 choices. History, 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 and history. But I put history 1, 2, 3 because they're all different books. And then science fiction 1, 2, and 3. So then once you take one of the books, then there's going to be 7 left. We don't know which one they're taking because we don't know which probability until they give us the probability. But we do know that the counting principle is going to say it'll be 8 times 7 because one of the history books is gone. So if that one's gone, if they choose that one and that one's gone, then there's only going to be 56 left instead of the original. Okay, so if we look at that, the probability of a history and then a science fiction would be, well, if that's gone, then there's only 56 left. So history and then science fiction. Let's see how many history, science fiction there are. So it would be this one in a science fiction, that one, and that one, there's 3. And then this history with 3 science fiction, there's 3 more. History with science fiction, 3 science fiction. And go on down the line, 3 more and 3 more. That's going to be 3, 6, 9, 12, 15. So it's 15 out of 56, which is exactly what they got by taking 5 eighths times 3 sevenths. But this is much shorter. That's it. Have a good one.